Go, thanks. Could I get someone near the back of the room to please close the door? Thanks. It's okay if they stayed inside also. Yeah. Okay, so, hi. Yes, we've already got an email. So I'm going to tell them about it too, yeah. No, not yet. We're just starting now. Okay. Sure. Thank you. So just before we start, this is Richard Stonehouse. We'll be taking some pictures of our working group today. So if anyone has any objection to that, let us know. I can't imagine there would be.
Get your face on copyright or anything?
You're in NetVC. I hope that's what you want to be in. Let's see. Note well. So we kind of went over this a bit on Monday, but just to make absolutely certain that everyone is aware, this working group, even more than others, has some considerations even in our charter around IPR. And although I am not your lawyer, roughly speaking, this means that if you know about IPR associated with anything that you're talking about, you have certain obligations to disclose that to the IETF. There's a form on the website for this, and you can read BCPs 78 and 79 for more information. And
in our first topic, we're going to have a brief intro on the IPR research and IPR declarations on that. And we'd just like to reiterate. Not loud enough?
Do you want to get up to a microphone? I can't.
We can't hear you. You can't?
That's the door.
Really? We hear huge. The speaker's pointing to us? Oh, that speaker's, is that? Okay. So the first presentation is going to include some IPR details at the beginning. So we just want to reiterate that we, while it's fine to talk anything about factual matters on IPR, we're not going to be discussing any evaluations of IPR or any opinions on the relevance of any IPR in the work group. So everyone is free to form their own opinions about the validity of IPR, but we won't be discussing it in the work group.
All right, and as usual, we've got blue sheets to hand around. Make sure you get your name on this before you take off. I need a note taker. I don't have Martin here today, so I have to find someone else. Can I impose on Brian, perhaps? Thank you, I appreciate it. And then I would need someone, scribe, I probably ought to change that. It's not really a scribe. We need someone to sit in the jabber room so that if there's any comments, they can be brought to the microphone. Thank you very much, Matt. Sorry?
And there may be nothing to do. That works.
Oh, that's true. We have the thing going on. All right, cool. This is the agenda. There's been one slight tweak to this in as much as we had 20 minutes at the end, and Tim decided that if that actually stays on the schedule, it'd be a good opportunity to talk about the results of the NetVC hackathon over this past weekend. So if you're not interested in that, you can go ahead and leave. If you are, and we have time, we're going to be going over that. And that's it. So, Cullen.
So, see if I can get a mic going here. So I'm going to talk for just a couple quick slides here about the Thor project and the IPR around them. Then after that, there'll be someone speaking about the actual technical details, far more importantly about Thor. So next slide, please. So the most important thing, oops, those are not the slides. If you downloaded them from the browser, the IETF can't make a website that works. So you have to refresh the cache frequently.
Oh, you need to send them to me then.
So it doesn't really matter much, it's fine. The important thing for me to say, the slide I was expecting, is we have made an IPR declaration on some of this, so I don't get any of the crazy matte starry-eyed looks or whatever. You can go read the IPR declaration. Of course, obviously, we intend this to be go towards the royalty-free stuff, and we'll probably be updating the terms on there towards time, because we've been looking at things like the Opus license, like the usual Cisco "Don't bug us, we won't bug you" type license, and we realized through the whole Opus codec working group process, it was valuable to have all the people who are contributing have a similar license. So we won't plan to work with people to update the license a little bit over time. So yeah, there's the slide I was thinking of. Thanks. Next slide. Now that I'm done speaking to it, we can go on back to the previous slides. Sorry. Yeah, next slide, I guess. So the way we've been looking at this work and doing it is we have a technical team that is developing the technical aspects of the codec. Obviously, this is a team that's worked, many of those people worked deeply in codecs for a long time and have a lot of IPR experience to understand the landscape. But they're taking the proposals and passing those over to the legal team. Legal team is trying to evaluate this because we don't think it's really possible for us to get towards a royalty-free codec without actually understanding some of these things. Legal team includes external and internal people, people with strong legal backgrounds, people with strong video codec IPR backgrounds that worked in the space for a long time. And I'll talk a little bit more about in the next slide about how they deal with this. But they pass back to the technical team both issues like, hey, we think there's a problem here in this type of area. It might have conflicts with this or that. And also can pass back information about IPR that might be useful to solve the same type of problem that they found when searching that's either old or IPR that they've managed to license in under ways that they think would be acceptable to the working group and meet the sort of royalty-free type terms. So next slide. The approach that we're taking to the IPR evaluation is to go gather lots of different patents that we think are worth reviewing and looking at. And we do this from looking at a combination of looking at existing patent pools, looking at companies that are well known to have developed IPR in this type of space, just general searches for words on them as well. And we gather up a big bin of stuff. And from that, we need to sort this into sort of tools that we're using and applying to the codecs under evaluation so that we can sort of bin them up. We figure out what our top tools are, and then we evaluate against the claims that we found against given types of tools, look at what we have, look at how it's working, and get the feedback from that. Let's see, there's anything I've missed to say about that. You can never be 100% done gathering. We've done a really strong game at gathered lots of stuff pre-2008, less post-2008. Obviously, those are equally relevant. Still in the gathering phase too. But we've got a big block. We've gone through a bunch of the tools. We haven't gone through all the tools we've wanted. But the thing that we've been discovering as we start evaluating these tools is where we found problems, we often found solutions as well, leading back to ways to change the idea or older ideas that had minimal or no impact on performance when we fed them back. This is an ongoing process. We have to do this as we keep iterating the codec and trying it. We view this going on over a long period of time. Certainly, The actual approach to the IPR validation, we're happy to share the risk in that and do that along with other companies. It's not something we'd expect a working group to do, but if other people want to do that under the right type of agreements, that's possible. Certainly we don't want to create an incentive for people to come and join and create non-royalty free IPR that we use. So that's basically what we're doing with the IPR on this Thor codec that we're going to present the technical stuff in a bit. If there's any questions on that, I'm glad to answer them. Okay, thank you.
Okay, thanks. So, Arnold, thank you. And the advice in the microphone that's been given is be a rock star. Go grab it and hold it. Thanks.
Okay. So I'm going to present Thor, which is a video codec that we have been developing within Cisco for the purpose of the work in this group. Next slide. So first, something about the design principles. We want to define a codec that has moderate complexity and can run in real time, software and hardware, and of course it's also possible to extend it to non-real-time purposes, for example 2-pass encoding. The basic building blocks are well known, so there are no dramatic changes compared to H.264 and H.265. On a very high level, it's the same block structure. Common design elements from modern codecs: larger block sizes, transforms, quarter-pixel interpolation. We do have some royalty-free Cisco IPR in the codec. We are trying to avoid non-royalty-free IPR, but of course, if other companies would declare their IPR as royalty-free, this could help improve the quality and the design of this codec. Next slide. So this is a very high-level block diagram of the encoder. It is exactly the same block diagram that you would find that would apply to H.265 and H.264. So at a very high level, the block diagrams are the same. Same for the decoder on the next slide. So you get the usual stuff: transform coding, entropy coding, intra and interframe prediction, loop filters, and temporal prediction. Next slide. So let's go into the details. The block structure starts with what we call a super block. That is a block by which you go through the frame in a raster scan order.
There's just a request that you actually stand in the box.
Yeah.
Thank you.
Okay. Sorry. Then each super block can be split into smaller blocks by a quad-tree structure. And then again, for interblocks, you could have split into multiple prediction blocks, and you can also have 1 or 4 transform blocks. So this is kind of similar to what you would find in H.265. Next slide, please. Yeah. So assume you do this quad-tree split, and you go down to the coding blocks that could have a variable block size, and they represent the nodes and the child nodes in your quad-tree structure. At that level, you need to signal a mode. And we currently have 5 modes. It's an intra. We have what we call inter 0, which is an MV index, motion vector index, and no residual information. Inter 1 is a motion vector index and residual information. And then inter 2, which transmits explicit motion vector information and residual information. And then we have a bipred mode that can do, basically sends 2 motion vectors. Next slide. We have 8 intra prediction modes: DC, vertical, horizontal, and 5 angular modes. Next slide. interprediction. Luma is using quarter pixel resolution, a 6-step separable interpolation filter, except in the center position where we have a special non-separable low-pass filter. Some of you might remember back to 2002, where Gisle proposed a special filter in one of the quarter pixel positions. Some people call that the funny position. And this is not funny anymore, but it's a special position and a special low-pass filter. And it gives some coding gain. For chroma, it's 1/8 resolution and a 4-step separable filter. And we do support multiple reference frames.
Tim Terryberry from Mozilla. So for the chroma filters, did you choose 4 taps just for complexity reasons, or was there an attempt to reduce ringing there as well? Tim Terryberry from Mozilla. For the chroma filters, did you choose 4 tap for complexity reasons, or was there an attempt to reduce ringing there as well?
The chroma filters are the same as in H.265. We haven't done any experiments to try to change them, but we might try something in the future. Next slide. Yeah, transforms. Those are the same as in H.265, HEVC, except that we added the 64x64 transform. There is a Cisco IPR on the transforms. They are integer approximations to the DCT. They are all sizes from 4x4 up to 64x64. And they have what we call an embedded structure, which means that the elements of the 4x4 transform matrix is a subset of the elements in the 8x8 transform matrix, and so on. Next slide, please. Deblocking. The deblocking filter is actually a lot simpler than both in H.264 and H.265. It operates on 8x8 block edges. There are on-off decisions per block edge and per pixel line, but there is no strong filter. And we have 2 pixel input and 2 pixel output. So it's, in some way, it's closer to the H.263 filter, actually. But it turns out to perform pretty well. Next slide. There is an additional loop filter that is applied after the deblocking filter. We call it constrained low-pass filter. It has fixed coefficients. There is an on-off switch per superblock. And in the encoder applies a rate distortion optimized decision process to turn the filter on and off. So this is kind of a replacement of SAO in H.265, if you want.
Jean-Marc Valin, Mozilla. The constrained low-pass filter, you're saying there's an RDO decision, so there appears to be some entropy coding there. Since it's a single bit, I assume it means that the entropy coding comes from jointly coding the low-pass filter with something else?
No, this is actually a single bit, which we send for each block, super block.
Okay. So you mean like, is there a rate? Like you're saying it's an RDO-based decision. Is there a rate part to this, or is it just a distortion-based?
No, it's a rate part because this 1 bit, you multiply that with your lambda.
Okay, but it's just 1 bit in either case. The cost of coding it is the same whether it's 0 or 1.
Yeah, you're probably right. So maybe it's only distortion.
Thank you.
Thank you for reminding me about that. Yeah. Okay, next slide. Entropy coding. It's at the moment it's VLC based. There is we are not married to that. If someone wants to contribute a good arithmetic coder, that would be interesting, and that is something we would be happy to consider. But at the moment, we have something that is at least very simple, low complexity, and it avoids a lot of IPR. But we would be happy to consider arithmetic coding also. As a consequence of the VLC-based approach, some of the block level parameters need to be coded jointly to get close to the entropy. For the transform coefficient coding, this is an improved version compared to what we had in version 1 of the HEVC reference software. That was removed from the software eventually because H.265 do not support CAVLC, but we have improved on that scheme since then. So this is what we use for transform coefficient coding right now. Next slide. Yeah, this is on encoder optimizations. This is a non-normative part that we build into our encoder to maximize performance. So for motion estimation, we use a fast search, SAD-based. The intramode selection can be either SAD-based or RDO-based, based on the complexity operating point. When we go down to the coding block, we need to choose the size of the coding block and the mode. That is RDO-based. Currently we have 3 operating points: high complexity, medium complexity, and low complexity. That is just a sensible collection of configuration files. There's no problem to have finer granularity on that, but at the moment we have 3 operating points. And we have done some SIMD optimization for some low-level functions, like transforms, motion search, motion compensation, interpolation. Next slide. Yeah. There are some planned extensions. We are currently working on reordering of frames, like B-frames. It is currently in the software, but we have not done a proper tuning yet. So today I'm not going to present any results on that, but it's in the software, but it's a bit immature. We are planning to add slices and tiles and maybe other parallel processing tools. Next slide. So for compression performance, I'm going to present some numbers. First, some slides on how we did the measurements. So we're using BDR, PSNR based as a metric. So far we have considered only HD format. So I'm presenting on the results on that. We haven't optimized for lower resolutions at all. So we have the JCT-VC class B and E plus 4 internal 1080p60 sequences. Next slide. Yeah. So we have been trying to compare Thor with X265 and VP9 using the HM reference software as an anchor. So 3 codec compared to HM as an anchor. So the HM is configured with what we call low delay B configuration, which is no reordering, no look ahead, and systematic QP variations. So the GOP structure is fixed. It's independent of the content. And Thor is using the exact same constraints. For VP9 and X265, that was a bit more difficult because it was not possible to configure those codecs to use the same GOP structure as HM. So this is not 100% apples and apples comparison. This was the most reasonable I could do with a low delay constraint. So the results are on the next slide. So what you can see here are 3 different codecs. And for each sequence and each codec, there is a number. That is a BD rate number, and it tells you how many % extra bit do you use compared to HM, the anchor. And if you take the average over all the sequences, you get at the bottom line. And what you can see is that 4 uses, on average, for the same PSNR, 22% additional bits compared to HM. VP9 uses 40% extra bit, and X265 uses 24% extra bits on average for the same PSNR.
Hi, Ralph, this is John. Yeah, since you didn't mention VP9 before, I'd like to have you send me email on the configuration used on that one. It doesn't fit my numbers comparing X265 and VP9.
You're saying the command line does not fit the other experiments you did? Could you say that again? I didn't understand what you said.
No, I'm saying
Okay.
that when I did comparisons between X265 and VP9, they were on the same order of magnitude, not that kind of difference. So please, I'll contact you about that later.
Yeah,
when I have figured out this one.
I mean, I would be happy to have discussions on this after this meeting. There's no problem.
Mosinati from the Flow Mic. I think, Harold, you did contact Jim Bankowski directly, right? And DeBarga gave you the settings to use for VPX encoding, right? The settings that could...
Yeah,
What was the CPU used, by the way? It's a $C on the screen.
I have in the table on the next page, CPU used is 0. Now I have additional results where I change the complexity setting and have different results. But these were the high complexity operating modes for all the codecs.
Okay, thank you.
But to go back, I have been in contact with people in Google to discuss these settings, and it seems like they have a preference for 2-pass encoding, which didn't fit the low delay constraints. So maybe that explains some of the differences.
So I think this kind of highlights the need for, in the testing draft, to have really good understanding of how to do apples-to-apples comparison among these codecs, and to give each of the codec teams, the onus of putting the best settings to make their codecs look the most flattering, so that we can do our testing and be fairly sure that we have good results and good numbers out of it.
Matt Miller, relaying for Randall Jessup. Interesting for for RTC Web use is the head and shoulder case. It would be interesting to hear why you think those results are happening.
Yes, I do have some thoughts about that. I think we have considered, we have paid a lot of attention to static scenes because this sequence has a lot of static scenes. So to represent large areas with as few bits as possible.
Yeah.
Next slide, please. We have also done some very simple complexity measurements. We choose to do it very simple. So we picked one sequence, one QP value or bit rate, and run timing on a single core. And when you do that, you get the results on the next slide. Yeah, so I should explain this. On the horizontal axis, it's the BD rate numbers from the table, at least the left point on each curve. So this shows number of bits in addition to the anchor. On the vertical axis, it's the frame rate for this particular sequence doing single core encoding. And there is one curve for each codec. And each codec has multiple operating points, from high complexity to the left and to low complexity to the right. And as you go along the curve, you increase the number of bits, but you also increase the speed of the encoder. And of course, the goal is to achieve something that is to the upper left corner of this diagram. Highest possible frame rate and as close to HM as possible, maybe even better. This is where we are today. I expect that we will improve in the next few months, certainly on the bandwidth axis, but maybe even more on the vertical axis, because we only just started this work to optimize for speed. So we hope that we can improve the blue curve significantly during the next few months, especially on the frame rate. Next slide. Yeah, just one line about the source code. It's available in this location, and so it's free for everyone to take a look at. Thank you.
Thanks. We have a lot of time at the end of the slot, so discuss.
Question, Xiaoqing. I have a question regarding your choice of using B-frames, but in the low delay mode, because I would suppose typically people would try not, sort of avoid the extra delay with B-frames. Can you explain, if you use that, what's the extra delay penalty you would introduce? And would that still fit into, like, what's the low delay part? How low latency can it support?
Yeah, if I understand the question, there was a combination of low delay and use of B-frames, right? You can have by prediction with prediction from 2 previous frames. So that would not add. If you do it like that, it would not add to the delay, and that's what we have done here. Excuse me? Yes.
So, Tim Terryberg from Mozilla. With regards to the entropy coding, so you're perfectly free to steal the arithmetic coder in DALA. It should actually be fairly easy to convert over, because we support raw bits, which are basically what you're doing now. So you could basically just find your put bits interface and replace that with the call to R's, and then convert symbol by symbol into using arithmetic coding. So that actually would probably be relatively straightforward to do.
Okay, thank you for that information, and we will consider that and try to find some people to do it also.
Anyone is free to try any experiment. It doesn't have to be the presenters.
I think we would be happy to help.
Steve Botsko from Polycon. Not a question exactly, just a comment. I think it's great that we have another candidate. I think it's looks like a wonderful piece of work. I like the fact that you're vetting the IPR so carefully. I like the attention to medium complexity. I think this will be very, very helpful for us to be evaluating.
So a chair point on the multiple candidates. I think we're pretty clear that the output of the working group is going to be a single codec, all right? So we need to make sure that we understand all of the candidates and all of their best parts and figure out the right technical solutions to arrive at a single NetVC codec at the end of the work group's work.
Yeah, just to clarify, I wasn't assuming anything other than that. But I think it's good that we have more options to be looking at.
And the group welcomes more. If anyone has codecs in their closets, please bring them out. Harold. It's in a very large data center's closet.
Okay. Well, thank you very much, guys. I appreciate you coming to talk to us, Harold. Let's go ahead and get, I think Nathan's up next. Yeah.
All right, so my name is Nathan Egge. I'm from Mozilla, and today I'll be talking to you about a draft that we submitted around one of the coding tools we're using in DALA. Next slide. So today I'll be talking about lap transforms, which are not a new idea. They were originally proposed for still image coding by Henrik Malvar in 1989. The idea is to apply a pre-filter across block boundaries that's invertible, that removes spatial correlation between the blocks. This pre-filter has two benefits. The idea is to improve coding performance, but also to be something that can be applied on the decode side to remove blocking artifacts. And this was originally used in audio, and the idea there was that blocking artifacts end up being something that are very audible, and so they needed a technique like this. It was not widely adopted in video because of some of the problems that come up with it. Let's go to the next slide, and I'll show you what this looks like. So the pre-filter, if you apply it to just an image, it ends up decorrelating adjacent blocks, and so your image ends up being blocky. That's what's shown at the top. If you compare what happens to taking an original image and applying just the DCT with quantization, you can see you get these blocking artifacts along block boundaries. If you take the same image, apply a pre-filter, the DCT, and the same quantization, and then inverse the DCT and invert the pre-filter, you'll see that those blocking artifacts are gone. These images are not meant to be a fair comparison because no coding was done for the quantized coefficients. It's just an example of the kind of artifacts that this technique removes.
And I'll point out that these are a lot easier to see on my screen than that one, so you all want to grab the slides and look at them to follow along.
Yeah, apologies for that.
The projectors aren't really set up for this kind of thing.
Okay. Great. So let me describe how we use these in DALA on the next slide. Excuse me. So yeah, the pros we have here for using lap transforms are you have a larger spatial extent. Because we're doing this lap transform that crosses block boundaries, the total transform, which is the lap transform plus the DC, has a larger support area, and so we end up getting an improved coding gain just by using the lap transforms. And we did an experiment where we took data from a set of still images and did some comparisons where we were using the KLT for 4x4 blocks everywhere as compared to the DCT, and you can see that the DCT gets similar performance. When we apply lap transforms in the KLT, we get the same kind of gain. So what's really fascinating about this is that on the 4x4 blocks, on smaller blocks, the benefit is almost a decibel. As you go to larger blocks, it kind of falls off. So at 16 by 16, it wasn't as huge an improvement, and for larger sizes, we found that it was an even smaller improvement. Another benefit is that the post-filter is non-adaptive. And so what that means is that we can take the inverse and apply it exactly as the pre-filter. And so this then takes the place of using an in-loop deblocking filter within the coding pipeline. The cons are, of course, that because we have the additional support area, this increases ringing on edges. And it has the other major drawback that many of the coding tools we use are now no longer applicable. So before, when you would use neighboring pixels to do intra-prediction, those neighboring pixels are no longer available to the decoder. And so being able to predict a block from its spatial surroundings doesn't work. And so in DALA, we had to come up with other techniques for that do not have the same benefit directly as doing spatial prediction. All right, next slide. So what we have support for in DALA currently is we have support for the following block sizes: 4x4 up to 64x64, which is in progress. Lapping is done basically on the Luma plane by applying the 4-point and 8-point filters. Yeah, so on the Luma plane, we can use 4x4 and 4-point and 8-point filters. We apply the 8-point filters across larger blocks and 4-point filters across the 4x4 blocks. When we split an 8x8 block down to a 4x4, we then apply a 4-point filter on the interior edges, and I'll show a demonstration of that shortly. For chroma in 444, we do exactly the same thing as we do in Luma. When it's 420, it'll use a 4-point filter everywhere. And this is so that the filters along block boundaries have the same spatial extent because we do things like chroma from luma and other prediction. And then the important thing to know is that the lapping size does not depend on the neighbor's block size. So as you recurse through your block size decision, the neighboring blocks, changing your neighbor's split decision doesn't impact the lapping along edges. And this allows us to then extensively search or exhaustively search all possible combinations of block partitions without the lapping interfering with neighboring decisions. Actually, so specifically, when we do the exhaustive search, we'll actually split all the way down to 4x4s, and then we'll compare a 4x4 or a set of 4x4 blocks to the 8x8 block that they would represent, and then take the best of those choices. And as we move up through the hierarchy, we'll compare merging all blocks together versus the best of the split blocks below that. All right, for the next slide, please. So this is the order we apply filters, starting at a superblock level, and in DALA we have 32 by 32 superblocks currently. We'll be moving to 64 by 64 superblocks. You'll apply the 8-point filter across the top and bottom edges. And next slide. You'll then apply it across the left and right edges. And then next slide. Then you'll apply it across the horizontal edge and then the vertical edge. And now you can recurse and do the same technique for all the interior edges of your blocks below that. So if you split to 8 by 8 from the 16 by 16, say, you'll continue doing the filter in the same fashion on the interior edges. All right, go to the next slide. So the lap transforms that we have in DALA have some very interesting properties. So we've designed them to be completely reversible. That is that for any input x, applying the forward lap transform followed by the inverse lap transform gives us the same value of x. This is important because we want to make sure that when you have similar content frame by frame, you would like to have the same values come out of your inverse transform so that there's no rounding error that's accumulated. Our transforms are bi-orthogonal, which means that the lap transforms introduce some scale factors. These scale factors have some correlation between the coefficients. We're not exploiting that correlation. There's a dynamic range expansion using these lap transforms. So the core DCT we designed as an orthonormal transform, which means there's a minimal range expansion on that. For the pre and post filters, they add about 1 or 2 bits depending on the scale factors. Because the DCT is done with an integer approximation for very small inputs, there's a lot of rounding. So we get around this by scaling all of our inputs up by 4 bits. And then after the transform, on the inverse side, once we've done the inverse transform, we'll scale them back down. This has the effect that for blocks larger than 16 by 16, we can no longer fit coefficients in 16 bits, and they'll have an impact on SIMD perhaps when we get to doing that optimization. Next slide. And that's it.
Mosinati as individual from Floor Mic. So can you describe what was the main motivation for exploring this? Was it the thought of deblocking IPR, or was it something else like expected coding gain even at the higher resolutions?
Yeah, so I think there were 2 things. One is in the audio field, this is used extensively everywhere because of the reduction in blocking artifacts, and so we already kind of had an idea that this might be something that's interesting. We thought that the coding gain might be a bigger deal, but it turns out at some of the larger blocks, the improvement by using the lap transform was reduced, and in particular, moving to these 4x4 or these 4.8 point only filters has kind of reduced it a little bit more. And there was some thought that this would allow us to, skip entirely some of the IPR around the deblocking filter. Although I noticed that Cisco has some IPR they're contributing, it may be possible to use that. So,
okay. And what was the point at which it was giving negligible gains? What was the like resolutions or block sizes where it started to taper off the gains?
I mean, the table I showed before, yeah. So, at 16 by 16, you get almost, 0.35 dB. So, like larger than that, it was kind of falling off even more than that. So,
okay.
Jean-Marc Valin, Mozilla. Actually, in some sense, the coding gains reported here are kind of misleading in the sense that, especially for large blocks, in practice, it is actually a place where lapping benefits the most because of the reduced blocking artifacts. For example, the 8-point lapping is wider than typical adaptive loop filters, so it creates less blocking on larger blocks, despite the fact that the coding gains that are like special theoretical measurements, they do not see that. And even on smaller blocks, despite the larger support, in some cases you actually get better edge behavior. So it's not as simple as looking at the coding gain and saying, oh, it's an improvement here, not there. That can sometimes be misleading.
Tim Terrier from Zillow. Can we go back to the coding gain slide? So one other interesting thing I wanted to point out about this is that if you look at the lap transform DCT 8x8 number, which is 14.12, that is already larger than the 16x16 DCT number for the same spatial support, which I also thought was interesting.
Mosinat again from Floor Mic. What Jean-Marc just said struck me as it may have better psi performance than some objective metrics currently show. Does that highlight the need for trying to find metrics that capture the artifacts like blockiness better in the testing draft?
I mean, certainly, yeah. I think that would be a useful metric to have specifically, but
are you aware of any work on that?
Jean-Marc Valin again.
I'm not aware.
Among the metrics we currently use for DALA on Are We Compressed Yet, one of them is called FastSSIM, and it is very sensitive to blocking artifacts. It has its own issues. It is by no means perfect, but I believe having many metrics is a good thing, and at least they can, when one behaves very differently from the others, it's at least a sign that one should pay very close attention to what's going on. I don't think we should really spend so much time researching new metrics because we might as well charter a new working group for that. This is as big as Codex. But we certainly should use existing ones and see which ones are indicative of interesting behavior.
Yeah, so Tim Terrier from Mozilla again, just responding to Mo. So Google has a metric that they designed to detect blockiness, and I'm sure there's plenty of other ones around there, but that particular one is open source, and we've looked at integrating that into our Are We Compressed Yet tool. It just hasn't happened yet, but we plan to do so.
Okay, thank you.
Thanks, Nathan. And next up, we have Jean-Marc.
So here I'm presenting some very, very early results for improving performance in screencasting operations. In screencasting applications. The draft that I submitted is implemented in the context of the DALA codec, but it would actually be applicable to pretty much any other codec because it's a completely separate coding technique. Next slide. So there's several properties that screencasting content has compared to normal photographic type video. This is a possibly non-exhaustive list. So the first property is the only one that I really addressed in this draft. And it is being able to properly encode anti-alias text without making too much of a mess out of it. And I'm talking about encoding in the pixel domain. I'm not addressing any sort of vector side channel. So there's others. There's other special properties. For example, the content tends to have many horizontal and vertical edges, like window borders and things like that. It tends to have a reduced number of colors, and at least in many blocks it does. There's also, in terms of motion, it tends to be rectangular because people move windows around. So that is also very common. I did not address any of these except for the first one. If you can think of others that we should consider, then I'd like to know.
Jonathan Lennox, yeah. Jonathan Lennox. The other, I think the temporal qualities of screencasting are also very interesting because you tend to have nothing happening for a very long time when all of a sudden everything changes at once. Basically, right, if you hit the next slide, boom, other than the white background, all the pixels just changed. But before that, it was completely static for 15 seconds or a minute or something. So I think that's the other interesting difference with screencasting.
Yes, I guess the simple window displacement should be even stronger in the sense that very often there's nothing at all. I agree, yes.
Mozanetti, I think, again from a floor mic, I think when people say screencasting, it's usually a very varied perspective of what the word means. Maybe we should highlight this more clearly in the requirements draft, but this could mean anything from what we think of presentation casting to wireless display. And of course, in wireless display, all bets are off of what the content actually is. It most likely is not just static. People don't present to themselves when they're when they're using their machines. So I think we need to be careful about what properties we're targeting for these screencasting modes.
Yeah. Well, one thing implicit that I should have mentioned also is that all of this should probably be switchable inside a particular frame. Like obviously, if you do remote desktop, you might have a movie playing somewhere, and you want to be able to code both in the same frame. So I think this probably addresses.
So, Jonathan, could I have you send to the list your comment about temporal behavior? Thanks.
Next slide, please. Okay, so the approach that I'm presenting here is based on the HAR wavelet. It is the very simplest wavelet one could possibly use, and it is absolutely terrible for use in any sort of natural images. However, it has interesting properties for the very specific case of screencasting, in part because it has very compact support, so it has reduced ringing compared to pretty much any other transform. So very quickly, on the left, you can see the actual mathematical definition of the HAR transform for a one-dimensional two-point transform. On the right, this is how the decomposition works in the example where you have a 2D transform of 4 by 4 points, so you have only a single DC over that block, and you have very localized basis functions, especially for the high frequencies. And this is the idea that for text, you want to reduce ringing, so you can do it that way. Next slide. So once we have the actual transform, we need to encode the quantized coefficients. And in terms of quantizing, this is done in with what I call the L1 tree wavelet encoding. This is based on the tree structure of the wavelet transforms, kind of similar to other tree-based techniques like the EZW, the embedded zero-tree wavelet. In this case, the main difference is that the tree is based on the sum of the absolute value of the entire tree. So the very first thing we encode is the sum of the absolute value of the coefficients for the entire block. And then we say this sum is just distributed between horizontal, diagonal, and vertical in this way, knowing what the sum is. And then for each direction, we start with the top level tree and we recurse down saying this is how the sum is split between the parent coefficient and all of the 4 children coefficients. So this is a good way to also represent cases where an entire location has all 0 wavelet coefficients. It actually performs slightly better than other techniques that were not based on the sum. And there's also some IPR issues that are made easier by working with the sum of absolute values. Next slide. So I hope this kind of shows up relatively clearly. This is really a magnified image of a screenshot that I took. The fact that it's magnified may change some artifacts, but it should give an idea. So I'm going to show 4 images at exactly the same rate. This is a crop of a much larger image that was encoded at the same size for all the different codecs. So this is what we get right now with JPEG. Next. This is what we get right now, or a few weeks ago, with the DALA lap transform based encoder. So it's not really great in terms of ringing. Lapping is really good for many things, but for text it is terrible. Next slide. So this is what we can get with the simple HAR scheme that I just presented. So you can see the ringing is much reduced on the text especially.
Mosenetic from Formic. Is this all constrained to the exact same number of bits? Is that what you're doing?
Yes, the total sum of the bits is exactly the same. Okay. The entire image is 1,000 something by 1,000 something, and the total size in all cases was 82 kilobytes.
And by JPEG, you mean original JPEG with no extensions like AC or JPEG 2000 or anything like that?
I mean original JPEG, okay. Encoded from GIMP on Linux, whatever it uses, probably not Moz JPEG. I don't believe this is Moz JPEG. So this is what we got with HAR, which has much less ringing around the text. And you can compare with, this is X265, which on text only images actually performed slightly worse than HAR. However, in this case it's better because it handles all of the long lines much better than the HAR transform, which is very localized. Especially all the icons look a lot better in 265, but at least the text with the HAR transform looks pretty good. Next slide. So in terms of objective evaluation, there is currently a screenshot test set in Are We Compressed Yet? Composed of about a dozen screenshots or so. It is very preliminary. It can probably be improved a lot. If some of you have a better test set that we can use, that would be very appreciated. What we have is just random things we got from Wikipedia that looked screenshot enough and weren't compressed before. In terms of metrics, on Are We Compressed Yet? We have PSNR HVS, PSNR SSIM, and Fast SSIM. And at this point, it is not clear whether any of these is any good on screenshots. So far, it appears that PSNR HVS is the least wrong, but I would not trust these metrics very much at this time. So I prefer looking at it so far. That's it.
Xiaoqing, two comments. One is regarding the comparison use.
Yeah, please get very close to the microphone. Thanks.
So two comments. One is regarding the visual comparison you show. I would assume that people might have preferred X264 versus the HAR, as you explained, even though you have text, sort of screen sharing with some text, but apparently X265, handles the mixture of content type very well, even when you're just, sharing a document.
So right now the comparisons that I'm showing here is based on applying the HAR transform everywhere in the image, which is actually not that good in many cases. For example, there are places where there's gradients and things like that which are really not well handled by HAR, and so that overall X265 actually does better than what I'm presenting here. The only of the test set we haven't already compressed yet, the only image where the HAR transform actually performed better than 265 is the only one that has only a lot of text and nothing else. And on that one, we actually perform better. On the image here, what happens is that the HAR code needs to spend a lot more bits on the icons and things like that. So it has to spend fewer bits than 265 on the text, and it gets its slightly worse. And again, this is like a first pass. It's expected to get better.
Yeah. So your plan would be to find a way to integrate two modes of compression within the same frame?
Yes, absolutely. Like this is an absolute requirement, because you cannot assume that the entire frame will be made of text. Some parts will be icons and lines, and some part will be just like natural content. And we need to be able to handle all of this, which is not at all implemented at this point.
Okay. Second comment is regarding the metrics that you've been trying so far. Based on my understanding, they were really designed to PSNR is a purely, statistical one. So aside from that, all the others, the SSIMs, are really designed to reflect statistics from natural images. So that's probably why from the very start, they are not good candidates to consider. It would be nice to consider things which match the visual characteristics of screen sharing, things like reduced color space, straight lines, etc.
Yeah, I absolutely agree. And if you have any metrics to propose that are actually good at screenshots, I would be very much interested.
I'm Mosenetti from the floor, Mike. So I was surprised that you were targeting anti-alias text with HAR, because I actually would have thought that just straight lines or non-anti-alias text would actually be where HAR outperforms. And things like 264 encoding, the more anti-aliasing you do, typically the better the encoding ends up looking. Have you tried this on something like an Excel spreadsheet with lots of sharp, horizontal and vertical lines and maybe not non-anti-alias text?
Yeah. So actually, things like spreadsheet is one of the worst issues we have right now with the HAR transform. And if you go back to the slide where I'm showing the basis functions, I believe is the third slide or something. Here. So what happens is our high frequency basis functions are very narrow. So if you have a line that spans the entire block, we have an entire line of non-zero coefficients. Whereas in the DCT, you can represent this more compactly. So this is one area of improvement right now that I'm looking at, like how to extend either extend the transform, use a different decomposition to be able to have more compact representation for purely horizontal lines. This would very much increase, like essentially the place where X265 does the best compared to what I'm presenting here is actually spreadsheets, because there's lots of horizontal and vertical lines for which the DCT is not so bad at representing, and HAR is absolutely terrible. So this is a known place that can actually be improved in what I'm presenting.
And I assume by X265, it's only implementing main profile, not any of the new candidates for screen content profiles, right?
No. It's the main one.
So the bar is probably higher now.
Totally. This is very early work. It needs to be improved very much.
All right. Thank you very much, John Mark. And now Tim's going to talk to us about the hackathon.
All right, thank you. So this weekend, we had a hackathon, well, for a large number of working groups, but one of them was NetVC. And then there we ran a bunch of experiments on both Thor and Dala, and I thought that would be of interest to this group. So first thing we tried to do was integrate Thor into ReCompressedJet, which is the website that we use to test Dala. So we had to disable B-frame support, which seems to be okay since it's not very well tuned anyway. But the reason for that is that the current implementation requires the frame count of the video to be a multiple of the GOP size, which is currently 12 frames, and not all of our videos actually met that requirement, so that would have screwed up our numbers. But we will get that resolved eventually. So next slide. So here is comparing the two codecs via PSNR. So the muddy yellow or whatever there at the top is Thor, and the blue line underneath it is Dala. So it's currently showing that Thor has a 43.5% rate advantage over Dala on PSNR, which is not too surprising since we have not optimized for PSNR and in fact intentionally done lots of things to make PSNR bad. So two of those things are we use quantization matrices and activity masking, and those are relatively easy to shut off. So we did. Next slide. And that reduced the gap to about 23.6%, which is a sizable amount, but by no means all of it. So according to PSNR, Thor is doing much better. So next slide. PSNR HVS, the results are a bit more mixed. So the BDR difference is less than 1%. But you can see that Thor is doing better at the low rates, and we are doing better at high rates. In particular, we're doing better at high rates that are probably so high that they're not actually practical. But again, it was more mixed. And then next slide. If we look at MS Fast SSM instead, then the story is the complete opposite. That it says Dala is 91% better than Thor, basically across all rates. And so I don't know what any of this means. This will probably involve actually spending some time looking at images and videos as opposed to staring at curves to figure out who's doing better in what scenarios and what conditions, etc. But the good news is that the two contributions do appear to perform very differently. So, we may be able to take the best of both and wind up in a much better place. So, next slide. So then we wanted to start to understand a little bit more detail, like what is responsible for the differences in performances. And so one experiment we tried was to basically take Dala and rip out all of Dala's motion compensation and replace it with Thor. So motion compensation in Dala is relatively decoupled, so this was actually a fairly easy experiment to run. We ran 4 different variations of this, which I'll describe in the next few slides. So if you recall the block diagram of Dala from Monday's session, what we basically did is took the OBMC block right there, next slide, and replaced that with Thor. So everything else is still running and still using Dala. So Thor forms the prediction frame, and we run lap transforms on that prediction, lap transforms on the input, send both of those to PVQ, and use all our quantization and entropy coding and all of that. So again, because this is running in Dala, it doesn't do any multiple references, it doesn't do any frame reordering, any of those things. So next slide. So for the first experiment, in Thor, we disabled residual coding because we're trying to use this to make a prediction for Dala. We disabled all of the intramodes because Dala does not have intramodes in its motion compensation. And we disabled 64 by 64 blocks because Dala's motion compensation only goes up to 32 by 32. And you can see from that Dala is about 24 to 28% better with a basically unmodified Thor, except for just shutting these things off. But this is not really a fair comparison. So in this case, the yellow line there is the Thor one, which is underneath the blue one. So Dala is better. But this is, as I said, this is not really a fair comparison, because Thor is spending a bunch of bits, in order to encode the possibility that it might use some of all these things, some of these modes and things that we've all disabled. So the next thing I did was go around and basically, disable coding bits for those things. So we stopped coding the coded block patterns. We stopped coding the split fags for 64 by 64, and reworked the mode tables to exclude all of the modes that Thor doesn't actually use. And that made between a 13 and a 14% difference between the Thors, so is now actually much closer, within 10% of where Dala is. And that was the second experiment we ran. And so typically you would expect OBMC to be doing with about 1 decibel better, which on the first slide was roughly where we were, but turns out when you disable all these bits, it's actually much closer than you might expect. So there may be room for improvement for us there. So next slide. So the third experiment we ran was to re-enable the intramodes and add them back to the VLCs so that we actually had the cost for them. And I should point out, by the way, that for all of these experiments, I didn't actually write a decoder. This is all changing the encoder only. So I could very easily have screwed something up in all this stuff. But we re-enabled these intramodes, and the numbers here at the top are comparing the previous Thor experiment to the current Thor experiments. This is not Thor versus Dala anymore. But it says just turning on those intramodes so that we have some kind of intra prediction in our motion compensation for places where the motion estimation is not going to do a good job, makes less than a 2% difference, which was somewhat reassuring, since the fact that we don't have this in Dala has been something that we thought might be a severe performance limitation for a long time. This is the actual performance limitation in Dala is probably a bit higher than this, but for various different reasons. But this at least gives you some kind of ballpark, and it was a 15-minute experiment. So it's nice to have a nice small and simple code base like Thor to run some of these on. Is doing this experiment in Dala would have been much more difficult. So next slide. So the final experiment was basically the cheating experiment. So this turns on all of the things in Thor that would make sense to turn on. So specifically 64 by 64 blocks, and also coding the splits for those again. And the surprising thing to me, at least, was that this still makes between a 7 and 12% difference, depending on which metric you look at. And all of that mostly shows up at low rates. The slightly curious thing is that at very high rates, you can actually see that made things worse for Thor. So again, these are numbers comparing the previous Thor experiment to this Thor experiment. But if you go to the next slide, that actually puts Thor ahead of Dala when you turn all of these things on. So that suggests there's some room to improve Dala there by adding 64 by 64 blocks, and hopefully we can get similar improvements out of it. All right, next slide. So one of the tools that Harold mentioned was Thor's constrained low-pass filter. Since this is just a loop filter at the very end of the processing chain, it was pretty easy to stick this into the very end of Dala's processing chain. So what we did at the hackathon was just a very simple hack where we have no signaling. So we decide on a super block by super block basis whether to enable the filter, but we didn't actually code anything to say whether or not we were doing that. We have better patches now that are showing real gains, but I don't have them on these slides. But the nice thing about this is that this was actually solves a long-standing quilting artifact that we had observed in fades at low rates, which is actually pointed out to us by Thomas Davies. So next slide. Good, and it actually shows up on the screen. So if you have a fade to or from black at very low rates, we would get what you can see as these quilting artifacts. So they actually show up as bright edges on the boundaries between blocks. And I can see that up here. Not sure if people in the back can see it. All right, good.
The projector is good at artifacts. It's very good at bad. It's good at bad, not good.
Yes. So that looks very not wonderful. And then we had done some analysis and we understood why this was happening, which is complicated, and I can go into it in detail if you want, but you probably don't want me to. But the best solution that we had come up with previous to this was to switch to 12-bit reference frames. So I believe as Nathan mentioned, we scale up all of our pixels by 16 before running them through our transforms, and then we scale them back down to 8 bits before storing them in our reference frames. Well, if you don't do that scaling back down, this artifact goes away. But that also doubles the amount of memory that you need for your reference frames and increases your memory bandwidth and has lots of other bad effects. So we thought maybe this constrained low-pass filter would be able to solve the problem without that expense, and indeed, if you go to the next slide, it makes this basically go away. So that was a nice positive development. And those were the results from our hackathon. So are there any questions? All right, great.
Awesome, thanks.
Great that you guys were able to hack away before the meeting.
Oh, thank you for getting us the code so we could.
People want commit, Colin James, if people want commit access or something in code, like, send me an email.
All right. That's all we had in our agenda. So you get 15 minutes to do whatever you want. There is one more set of blue sheets out there somewhere. If you have them, please hold them up in the air and I'll come grab them.
And anyone that hasn't had a chance to sign, feel free to come up and grab and sign.
And that comes down to the I'm not your lawyer. Thank you. I'm very amused that they make that look like the old thing you had to carry around on your keychain.
You'd be surprised the intelligence of people that have to log in.
Right? How many would you like? Oh, no, sorry. Which one do you want? Awesome. Thank you very much.
It's behaving weirdly, so
grab it before it dies.
I hope so. Like, I don't know what's going on.
Thanks. Appreciate you being willing to be shanghaied.
Anybody with a blue dot is a sucker.
I know. Well, blue apparently is not an option anymore. That must be popular. I'm not sure why you would want to put something blue on your badge. That could end badly, but.
So why don't the note takers get stars? They should get the stars. Oh, they do. Oh, it says
we can give it out to anyone we want. As chairs, we use our discretion. So in fact, I should have stuck one on Ryan just now. And as I was joking with Martin, he gets 2/3 of the star.
For sleeping?
for taking notes and being awake for 2/3 of the meeting.
A 4-point star.